All right, so for today's discussion, we're mainly going to be focusing on the full SVD and the geometry of the SVD, how we can view the matrix A as a set of geometric operations. So a lot to go over today, but let's do a quick recap of what we've been doing so far. So we were first introduced to the singular value decomposition of a matrix A with rank R as a bunch of outer products, a bunch of sigma I, ui, and vi, a sum of a bunch of those. And each of those were called rank 1 matrices. And vectors ui and vi were special because they were orthonormal. And the sigma i's, you could think of them as weights on the matrix. So this kind of told us which weights and which outer products are more important than others, which led us do a bunch of things like compressing images and stuff like that. So that was how we first saw the SVD. But I think in lecture, you were then introduced to the full SVD, which will be really the star of the show for today. So the full SVD is kind of different from the SVD over here. We like to call this one the sum of outer products from 1 to R as the compact SVD, since really we're just writing it out in terms of the R outer products. And the important part of the full SVD is that it's called the full SVD because these U matrices and V matrices are full M by M and N by N matrices. And these full matrices will give us some leverage when it comes to like the geometry of the SVD. And the sigma matrix over here is going to be an M by N matrix. It's not a square matrix, but the S matrix here, you might recall that S is a diagonal matrix. So we're going to have a diagonal matrix, and then we're going to have zeros padded around it. So it's going to give us the full SVD. And the only real distinction between the compact and full SVD is, well, we're going to add a bunch of terms here. Sigma R plus 1, UR plus 1, VR plus 1, all the way up to sigma N, UN, VN. And for all practical purposes, sigma I is equal to 0 for I greater than R. Like all these sigmas will be 0, but they will still have associated directions. And we're going to kind of use that to build the full SVD and see how to take advantage of those directions. So any questions about the compact or full SVDs? All right. If we don't have any questions, it's gonna recap how to compute the SVD and also show how to compute the full SVD of a matrix. So I believe you saw how to do this on Monday in discussion, but the way we did this was to compute the eigenvalues and eigenvectors of A transpose A. And I know some common questions people have asked are like, when do I use A transpose A or AA transpose? And you can use either matrix for either approach. Like A transpose A will always work, but if like M is less than N, then AA transpose will be more computationally efficient. And in this case, we're going to find eigenvalues and eigenvectors lambda I, ui. So the only real difference between A transpose A and AA transpose is a computational difference, but for all practical purposes, you could always use A transpose A and get the same result. And then what we do is we compute the singular values, sigma I, as the square root of the lambda i's. And after that, we compute the left singular vectors. So we computed the vi's as eigenvectors of A transpose A, but we can compute the ui's by using the A matrix and the vi's. So you can use the relationship A vi is equal to sigma I ui to say that ui is equal to avi divided by sigma I, since sigma I is a scalar. And we do this for like I equals 1 through r, where sigma I is greater than 0. If we were to use the other method of the SVD with AA transpose, since we computed the ui's, we would need to compute the vi's. And in this case, vi would be equal to A transpose ui divided by sigma I. So it's just a distinction of whether you compute the u's first and then the v's, or the v's first and then the u's. And last thing we do, well, since like all of this stuff should have been like reviewed for Monday. This was the compact SVD. For the full SVD, we want to find the singular vectors to complete the U and V matrices. Sorry, I have a really bad cough here, but to finish up these U and V matrices, we're going to realize that sigma I is equal to 0, so we can't quite divide by sigma I. But what we do know is that the, I guess, singular vectors corresponding to singular values of 0 correspond to the null space of A and the null space of A transpose. And this is something I believe we're showing on the homework this week, where the VI's span the null space of A. So in other words, what we can say is we can say that like if you want to compute the ui's for like, if you want to compute ur plus 1 all the way up to un, we can compute an orthonormal basis for the null space of A transpose. And by similar fashion, we can compute the V vectors by finding an orthonormal basis for the null space of A. And like how you compute the orthonormal basis, like lots of ways to do it. Like you can either like just like find the basis for the null space of A and just like perform Gram-Schmidt on it, or like use some algebraic manipulation to do that. Like I don't think we're gonna emphasize like the actual computation of how to do this orthonormal basis too much in this class, I think, for this semester. So if we do, we'll make clarifications about that. But any questions about the entire full SVD computation process here? The most important takeaway here is that like you can compute these UI and VIs by computing orthonormal bases for these null spaces. All right. We don't have any questions about this. Let's take a look at the full SVD. So I think I've hinted at it multiple times, but the real important part of the full SVD is this fact that the U and V matrices are square and have orthonormal columns. And sometimes we call these unitary. And what this does is this lets us view these matrices as rotations, because if you take a vector x, you multiply it by u, which has orthonormal columns, it's just going to rotate the vector x. This is like a visual of what happens. You have a vector x and you multiply by u, it's just going to rotate it. And as a result, we're going to see that the norm of x is equal to the norm of ux. So if you intuitively rotate a vector, it's not going to change the norm of the vector. It'll change the direction, but it will not change the norm. An orthonormal matrix doesn't have to be a rotation in higher dimensions, right? It could be another symmetry, such as a reflection. Let me think about that. I think potentially, yeah, because if you take, like, I was just going to say, like, if you take 1, 0, 0, 0, 0, 1, and maybe if you just swap all the columns of a 3x3 matrix, then yeah, you may be able to come up with some counterexample with a permutation matrix where you do some sort of like symmetry, such as a reflection, but yeah, I think it could be a rotation or a reflection. But in either sense, I guess what we want to emphasize is that it doesn't change the norm of a vector. And good, Mickey clarified that in lecture as well. So what this lets us do is it lets us view the matrix A as 3 operations. So like the full SVD of A can be written out as U sigma V transpose. And now let's think about A as some linear transformation that maps vectors x to y. So we're just going to say y is equal to ax. So A maps vectors x to y. And you can think of this as a series of a rotation, some scaling, and a rotation, or even a reflection. So a rotation or a reflection. But I think for all practical purposes, we're just going to call them all under the term rotations. So let's see. To give kind of an explanation to this, we have the vector x multiplying by V transpose. V transpose is an orthonormal matrix, so it's not going to change the norm. It's just going to do some reflection or rotation. And then we're going to scale by sigma, and x is going to be here in Rn. We're going to rotate it, so we're still going to be in Rn. We're going to scale it, and by scale here, sigma is not a square matrix, so sigma is an m by n matrix. So we're going to end up with some other vector in Rm, and then we're going to rotate that into another vector in Rm. So we can break down the SVD into these 3 geometric operations, and it's going to be the key behind today's discussion. So any questions about this geometric interpretation of the SVD, where we rotate, scale, and rotate? Okay. Let's take a look at, let's take a look at the discussion worksheet then. So the first question on the worksheet, we're going to take a look at a matrix A, and we're going to see how we can view it as a series of like rotations and scalings. And luckily it's a square matrix as well. So I'm going to give everyone some time to take a look at this, think about this, and we'll look at this together in a minute or so. Okay, let's take a look at this. Sorry, my cough is really acting up now. I was feeling a little sick last morning and might be getting a little worse, but all right. In my worksheet here, there are two plots. I think the official one doesn't have two. I just copied one over. But the reason I did this was so I could draw out the unit circle here, S. So S is the unit circle. It's cosine of theta and sine of theta from 0 to 2 pi. And we want to take a look at what AS, so if we take every vector on the unit circle and multiply it by A, what that image looks like. And I'm not going to do it for all vectors because obviously it's not possible, but like to do like computationally, but we can take a look at a couple of vectors. I'm going to take a look at standard basis vector E1, which is 1, 0, and E2, which is equal to 0, 1. So let's take a look at that first. So if we take the matrix A and we multiply it by 1, 0, then we can see that the resulting matrix multiplication is going to be 0 and 3. So this vector E1 gets mapped to the vector 3 and 1, or sorry, 0 and 3. And if we do the same thing for E2, which is 0 and 1, then the resulting matrix multiplication, well, we're going to end up with -1 and 0. And that's going to mean this vector over here, E2, gets mapped to the vector -1, 0 over here. And you might start thinking that since we have a circle here, if we take some linear transformation on that circle, it's got to be circle-ish or really an ellipse. So intuition should kind of say that we should have some sort of ellipse as the image. But just to kind of confirm our suspicion, let's take a look at one more vector. I'm going to pick one over here, which is, I'm just going to call this vector x, which is equal to minus square root of 2 over 2 and minus square root of 2 over 2. And if we do the matrix multiplication once more, we'll end up seeing that this becomes the square root of 2 over 2 and 3 square root of 2 over 2. And if we plot this, this is going to be somewhere, let's see, down here. So this was A, E1, A, E2, and AX. And we do it for all the vectors. You should get some sketch of an ellipse like this. And yeah, it's negative square root of 3 square root of 2 over 2. And if you want to prove this in a more rigorous fashion, well, what we can do is we can just start with 0, -1, 3, 0. Take cosine of theta and sine of theta. And the resulting matrix multiplication is going to be minus sine of theta and 3 cosine of theta. And if you remember back to like high school trig, this is like a polar coordinate like parameterization. And this should actually sketch an ellipse for theta in 0 to 2 pi. So it's kind of why it works the way it does. So any questions about anything we've done so far in this part here? I think the pedagogical approach here is kind of to work backwards as well, where we're going to first look at what A times the unit circle looks like, and then we're going to use the SVD and kind of look into why it was the way it was. So the SVD approach will come next. All right, if we don't have any questions, let's move on to the next part, which is to compute the SVD of A. So I'm just going to write out the matrix A over here, and I'll give you all some time to work on this. It's a fairly just computational practice, but it should be review from Monday. So kind of here to get you some review on how to compute the actual SVD of a matrix. And notice that by writing out U sigma V transpose, we're really referring to the full SVD. But here, we're not going to actually have to do any like null space filling. All right. Okay, so to go over this problem, it's really just a rehash of all the steps we talked about when computing the full SVD. So we compute the eigenvectors and eigenvalues, we take the square root to compute the singular values, and then we compute the left singular vectors. So let's start with step, I like to call step 0 really, which is to compute A transpose A. So if we do this, we're going to end up with 9, 0, 0, and 1. And it's just a good sanity check to always make sure that the matrix A transpose A is symmetric. If it's not symmetric, that means you've probably done something wrong in your matrix multiplications. Next step is to compute the eigenvectors of A transpose A. So since this matrix is diagonal, we can very easily see that lambda 1 is equal to 9 and lambda 2 is equal to 1. And always, always, always remember to order these eigenvalues from largest to smallest. So 9 is larger than 1, so lambda 1 is going to be 9. And then to compute the eigenvectors, we can look at A transpose A minus 9i, which will then be 0, 0, 0, 1. So the null space of this matrix, we can say that V1 is equal to 1, 0. And if we look at A transpose A minus I, sorry, I made the same mistake I made in my earlier discussion. If I subtract by 9i, it should be negative 8. Then we're going to end up with 8, 0, 0, 0. And the null space of this matrix is going to be 0 and 1. So we've computed our eigenvectors and eigenvalues. And what do we do next? Well, we've got to compute our singular values. So we've got to compute the singular values by taking the square roots. So we compute sigma I, which is the square root of lambda I. And we can do this as well. sigma 1 is going to be the square root of 9, which is 3. And sigma 2 is going to be the square root of 1, which is 1. And then we compute the ui's, the left singular vectors. And we can recall that AVI is equal to sigma I ui. If I have time, I might show how that formula comes from. Someone asked about it earlier. But we know that ui is equal to AVI over sigma I. And just to save ourselves some time here, you might notice that V1 and V2 are 1, 0, and 0, 1. And earlier, we computed what AV1 and AV2 were. So we did these computations already. So let's just save ourselves some time and copy our results from over here. If we hadn't done these computations, we'd have to do them, though. But since we have these results, U1 is going to be equal to 1 over sigma 1, which is 3 times 0, 3, which is then just 0, 1. And U2 is going to be equal to 1 over sigma 2, which is 1. And our other singular vector here was minus 1, 0. So we have minus 1 and 0. And we end up with minus 1 and 0. So last thing to do is to, well, for the full SVD, we need to look at like the 0 singular values and compute the null spaces. But here, this matrix is full rank, so it has no null space. So you don't have to actually do the null space calculation. To give an illustrative example, if we were to, let's say, suppose A transpose A was a 3 by 3 matrix with a 0 here, with an eigenvalue of 0, then you would compute the null space of A, and that would give you an orthonormal basis. But I'm not going to actually do that here, and I think to summarize the result, we can say that A is equal to, there are two ways to write this. We can write this as the outer product form, or, sorry, my u vector is minus 1, 0, or we can write this out in the matrix form, which would be u sigma. Remember, it's a diagonal matrix with a singular values, so 3 and 1. And then we have, let's see, our v vectors are 1, 0, and 0, 1. And we got to take the transpose of that. The transpose of the identity is the identity. So this is going to be u sigma and v transpose. All right. Now that was a lot, but any questions about the process of the SVD? Okay. We don't have any questions about how the SVD works. Let's now take a look at the geometric interpretation and how this SVD is going to relate to all that rotation, scaling, rotation stuff we just talked about. So now it's asking us to consider the columns of the U and V matrices, and let's kind of re-examine our plot that we drew up here. So we're going to do this together, and I'm just going to redraw what AS looked like. Remember how we had an ellipse with axes at 3, 0, 0, 3, and minus 1 and 0. And really what these vectors represented were the, I guess, what's it called? Left singular vector scaled by the singular value. So you can show that this is actually equal to sigma 1, u1, since sigma 1 u1 was like 0 and 1, so it's going to be equal to 3 times 0 and 1. I don't know if there's too much of a point to do this. I think it's more important that you understand the other interpretation I'm going to give, which is to really view this entire process as a rotation, a scale, and a rotation. So what we're going to do is I'm just going to kind of give a visual of what's going on here. So we're going to take a look at the journey the identity basis vectors take. And if you know what happens to the standard basis vectors, then you know what happens for every vector, since like they form a basis for the space and you can just take linear combinations of those. But let's say we started with just two standard basis vectors, E1 and E2, and we multiplied this by V transpose. So if we multiply this by V transpose, you can think of V transpose as some sort of rotation in the plane. And it's because it has orthonormal columns. And since the identity matrix is, well, the identity matrix, you can think of it as a rotation by 0 degrees. And I think just to recap, it might be good to write out what the rotation matrix is. You might remember from 16a, where the rotation matrix is of the form like cosine theta, minus sine theta, cosine theta. So you can think of the identity matrix as a rotation by 0 degrees. So if you multiply the standard basis vectors by V transpose, then V transpose E1 and V transpose E2 are going to be the same thing. You're just going to rotate by 0 degrees. Then we're going to scale by sigma. And if we scale by sigma, then, well, we can see that this lets us scale each of these vectors. And since these vectors are only pointing in one direction, really, and I guess what we're doing here is, I think it's kind of subtle because we haven't actually like given a different example for V that wasn't the identity, but we're going to rotate X to some other space where they can get stretched by sigma. So we're going to stretch these vectors. And sorry, since it's like 3, 0, and 0, 1, this means we stretch E1 by 3. So we're going to stretch it by some amount. So we're going to have sigma V transpose E1 and sigma V transpose E2. And then last thing we're going to do once we stretch these vectors is to multiply by U. And that U is going to be a final rotation. So if you look at this matrix over here, the U matrix, you can see that it has orthonormal columns, but more so, it's a rotation by 90 degrees. So we're going to rotate this like ellipsoid structure here. If we were to continue drawing out the ellipsoid, kind of forgot about it, but we then rotate this ellipse by 90 degrees. So we rotate it 90 degrees counterclockwise to end up with our final result. So we're going to have U sigma V transpose E1 and U sigma V transpose E2. And if we were to do it with any vector X, we would just follow the same process where if X, let's say, were some vector like this, then X would follow the same journey. All right, any questions about what's gone on in this geometric interpretation here? I think the main takeaway is that like the SVD, the matrix A, U sigma V transpose is just rotation, scaling, rotation. Pretty sure you're sick of this by now. So like for the sake of time, I'm going to skip the next part as well, because the next part is going to ask you to do the exact same thing, except your U matrix now, I think here is a rotation by 45 degrees or negative 45 degrees, I think. So if you do the same process here of just rotating, scaling, and rotating, you'll be able to see the results. And I challenge you to maybe take a little more interesting of an example where I think might be worthwhile to look at what this matrix would look like potentially, where instead of the identity, we have some other transformation. So maybe this should be a square root of 2. It should be minus square root of 2. Yeah. So try this out and see what happens. Okay, so last part of the discussion. A lot of this is going to be more helpful for the homework, so I really wanted to get some time to go over this part or this question as a whole. So we're going to talk about the SVD and the induced norm, and the induced norm, really what it is. If y is equal to ax, like what is the norm of y and what is the maximum over all x of the norm of y. So that's what the induced norm is trying to do. And we're going to use the SVD to do this. So give everyone some time to work on this. Hopefully part A should be a very short one, but nevertheless, take some time to think about this. Okay, so let's go over this one together now. And here we're really showing the result that a unitary matrix, one with orthonormal columns, doesn't change the norm of a vector. We've kind of stated this result multiple times throughout the discussion, but let's just finally give a proof for this. So it's good to recall that the norm of a vector, W, is equal to, maybe it's better to look at the norm squared of a vector, is equal to the inner product with itself. In other words, the norm is just the square root of the inner product with itself. So the norm of ux is going to be equal to the square root of the inner product of ux with itself. And if you recall the definition of an inner product, this is just ux transpose ux, which you can then expand out as x transpose u transpose ux. And here we're going to use the fact that u is unitary. So u transpose u is equal to the identity. And this tells us that this is equal to the square root of x transpose x, which is then just the norm of x. So we've indeed showed that a unitary matrix doesn't change the norm of a vector because it's some sort of reflection or rotation. Okay. If you don't have any questions about this part, let's take a look at the next part. And I'm gonna copy this over here because this is probably the most important thing to keep in mind while we do this problem of like, what is the norm of AX and how do we maximize that? So part B is asking you to find the maximum of the norm of AX in terms of the singular values. So I think it's probably a better thing to do to first consider the norm of AX, and something that you're most definitely going to need is the SVD of X. So give you some time to work this out on your own, and I would focus on finding what the norm is first and then figure out how to compute the maximum. Okay, let's take a look at this one now. So we have the norm of AX. Let's try to figure out what that is first before we actually compute any maximums. So first thing we do is to, well, let's just literally plug in the SVD. So we're going to have U sigma V transpose X. And next thing to realize is we have a U in front, which has orthonormal columns. So let's get rid of that, since we know that an orthonormal matrix preserves the norm of a vector. So this is going to be equal to sigma V transpose X. And from here, this is probably where the challenge might start to arise, where we have sigma V transpose X, but we can't really get rid of this V transpose. But something insightful you can notice is that V transpose X is a rotation of X. So V transpose X is a rotation of X. So what you can do is define Z as a new variable equal to V transpose X, the same way we did in change of basis and diagonalization, really, because V transpose X is V inverse X. And this is going to be equal to the norm of sigma times Z. And now let's take a look back at what our maximization problem was. And we wanted to maximize over all X with norm 1. In other words, we're maximizing on the unit circle. The norm of AX. And if we're maximizing over every vector on the unit circle, and we apply some rotation to it. So if we apply like V transpose X, it's not going to change which vectors we're looking at. We're looking at all these vectors. We rotate all of them. We look at them again. It's not going to change like the actual problem. So we can maximize over all Z with norm 1. This is going to be the same problem of the norm of sigma Z. And now, if you have an idea, type it out in the chat. What do you think the optimal Z will be? The optimal Z will be, remember that the sigma matrix, might be better to give myself more room here, has all the singular values. And we're constraining this Z to have norm 1. So Z times sigma 1 maybe. The first right singular vector. Yeah, I like all these ideas. So Z is going to be equal to, well, you can think of these as weights. So if you're multiplying sigma by Z, you can think of this as the same thing as like sigma 1 through sigma R and zeros around it times Z. And since Z has norm 1, like you can only put so much weight on each of these like values and on the values of Z. And since these singular values are ordered from largest to smallest, like the intuitive strategy here is to put all of our weight into the largest singular value, sigma 1. So we're going to put all our eggs into one basket. So the optimal Z is going to be 1 and then all zeros. And you can verify this as norm 1 as well. And the actual norm, the norm of sigma Z, will actually be equal to sigma 1. So this is going to be the induced norm of a matrix, the maximum value that it can, like the maximum value the matrix A can scale any vector X by. So last thing we got to do is to find the X that maximizes the expression above. And we saw that Z was equal to 1 and all zeros. Sometimes in the literature, we like to call this E1. So can we prove the choice of Z is optimal? Yeah, we can. Like, it's because these singular values are ordered from largest to smallest. Like, you can do it by contradiction, where if you assume there's any other weight on these zeros, like you assume, and I don't want to get into this too much, but if you assume like any weight, if you assume an optimal solution with any weight on, I'm just going to call these like Z1 through Zn, on Z2 through Zn, then you can actually show by contradiction that like that is no longer optimal, because you can put more weight into sigma 1 to make it like an even larger value. Anyway, and if you take E127, you'll look at all this. So we defined Z is equal to V transpose X. So the last thing we got to do is to kind of solve in terms of X, same way we did in like change of basis with multivariate diffie Qs. And since we know VV transpose is the identity, since V is orthonormal or unitary, we can right multiply by V. So we're going to end up with X is equal to VZ. And this tells us that if we were to write out the columns individually, take the first standard basis vector and multiply these two out, you can show that this is equal to V1. So there we go. We've shown that the first right singular vector maximizes this quantity, the norm of AX, over all vectors X on this unit circle or unit ball if we're in higher dimensions. So if you have any questions, definitely feel free to ask now. It is 12:01, so discussion is officially over, but I'm sure you may have some questions. So, all right. Thank you all for coming out today, and the recording I'll end here, but again,